That doesn't look great. Let's try to increase that gain. That's better. Let's try to increase it even more. So maybe even more? No, that doesn't look great. Maybe there's a better way to tune it? Hi, I'm Łukasz and welcome to the next video about active disturbance rejection control. In the last video we introduced second-order error-based ADRC scheme. You can see its equations on the screen. It's relatively simple, yet it has 5 tuning parameters, 3 observer gains and 2 controller gains. Finding the proper values of these parameters and how they relate to each other might be a challenging task in that blindly. In this video I will show you how to do it using very common and simple method of bandwidth parameterization. We'll go through the whole derivation step by step, so you can use the same procedure for any other linear ADRC system. Let's start with the extended state observer. Its goal is to estimate the extended state, in other words, to minimize the error between the real state and the estimated state. We can now define 3 estimation error variables, one for each state variable. We'll call them epsilon1, epsilon2, and epsilon3. How can we tell if epsilons will converge to 0? We can do it by analyzing the dynamics of the system in terms of estimation error variables. If the system is stable, the error variables will converge to 0. I assume you already know how to analyze the stability of the linear system and what is the characteristic polynomial. Let's start with the epsilon1. From the system dynamics we know that xc1 dot is equal to xc2 and xc1 hat dot is explicitly given in the observer dynamics. Just don't forget to change the sign. Now you can notice that the equation includes terms that are equal to epsilon1 and epsilon2. Let's substitute the terms and simplify the equation. Follow the same procedure for the epsilon2. This equation includes control input u twice, fortunately with opposite signs, so they cancel each other out. Now we can once again do the substitutions and simplify the equation. Epsilon3 dot is a little bit different. We don't know the total disturbance psi star and its derivative, so we leave it as it is. However, z star dot is defined by the observer dynamics and we can proceed as usual. Now we have 3 equations that describe the dynamics of the estimation error variables. You can now see them cleaned up and prepared to be rewritten in the matrix form. Let's do it then. I will call the matrix AE and artificially extend the total disturbance derivative into the vector form. All that leads us to the following equation of a linear time invariant system. We'll treat the total disturbance derivative as an input to the system and assume that it's bounded. Let's now calculate the characteristic polynomial of the system, which is given by the following equation. It's a third-order polynomial, so there are 3 roots corresponding to the poles of the system. How do we place them? The bandwidth parameterization method provides a simple answer. Place all poles at the same frequency. For the observer, we'll call it omega O. Omega O can be treated as a corner frequency defining the bandwidth of the observer, hence the name of the method. Let's now expand the right-hand side of the equation and compare it to the left-hand side. By comparing the polynomial coefficients on the left and right-hand side, we can find the values of the observer gains. And that's it. We reduced the number of tuning parameters from 3 to 1. Things are a little bit easier with the controller. We don't need to introduce any new variables. We already have xe1, xe2, and equations that describe their dynamics. What we need to do is to substitute the control law into the dynamics. We don't know the total disturbance, but we'll assume that the observer does its job well enough so that the psi star is cancelled out by the minus z star term. The assumption of good enough observer lets us also replace the state variable estimates with the real state variables. Now let's write the same as a matrix equation. This time let's call the matrix AX. Not surprisingly, we arrive at the LTI system equation for the controller. I'm pretty sure you know what to do next. This time we have a second order polynomial, so there are two roots corresponding to the poles of the system. Once again, both poles can be placed at the same frequency, which we'll call omega c, or controller bandwidth. Let's expand the right-hand side of the equation and compare it to the left-hand side. And that's it. Well, not really. We have reduced the number of tuning parameters from 5 to 2, but how do we choose the values of omega c and omega o? There's no easy answer. You need to actually tune it to the controlled system. Controller bandwidth needs to be high enough to ensure good reference tracking performance and disturbance rejection. However, it can't be too high as it may lead to instability or poor noise rejection. Observer bandwidth should be higher than the controller bandwidth. Typical values are from 5 to 10 times the controller bandwidth. Otherwise, the observer won't be able to estimate the state variables fast enough, and the controller won't be able to react to the disturbance and reference changes. Let's now see how it works in our simulation. Okay, we start with the same setup as for the error-based ADRC. Notice that our external disturbance has the angular frequency equal to 3. And what is changed is the extended observer is now parameterized by omega o. And you can see that lambda 1, 2, and 3 are calculated accordingly to the formulas we derived. And same goes for the controller, where we have omega c and the formulas for calculating kp and kd. And now when I instantiate the controller and observer, I need to provide the controller bandwidth, which I set here to 10, which is more than 3 times higher than the external disturbance. And I have the observer bandwidth, which I set to 50, which is 5 times higher than the controller bandwidth. And if we check the performance, we can see that there is excellent tracking and even lower integrated error than we seen in the previous video. But of course, there is some price for it. If you check the this peak control value, you will see that this is higher than what I had in the previous video with the, let's say, brute forced gains. And of course, you need to remember that if you make those bandwidths too low, you will not get the proper tracking. And the same goes with the bandwidth of the observer. Like too low bandwidth will result in the lack tracking and the poor performance. I don't think there is much point in trying to push those values more here in this example, because this is kind of idealized setup without delay, sampling, etc. So in the real case, this plus noise would limit how much you can push it. But still, instead of trying to find 5 parameters, I have only 2. Let's summarize what we've done this time. We've derived the characteristic polynomials for the error-based observer and controller. We've used them to demonstrate the bandwidth parameterization method, which places all poles on a given frequency. That allowed us to reduce the number of tuning parameters from 5 to 2. We've discussed the choice of the observer and controller bandwidths and how they relate to each other. Finally, we've shown how the bandwidth parameterization method works in the simulation. What's coming next? I'm planning one more video in this series, which will cover some aspects I skipped so far for the sake of simplicity. First, I'll introduce the critical gain B0 in the planned model. Then, I'll show you how to implement the error-based ADRC in the smarter way. Finally, I simulate the new implementation in Xcos, which is a free and open source software simulating alternative. Thanks for watching!